Hello students. Our goal today is to develop the algorithms to compute the strongly or to get the strongly connected components in a directed graph. And the way from now until we get to the point, we're going to pass through several important things, including topological sorts and classification of special components, certain components that plays an important role. Let me recap on a couple of points that we made in our last video, and they're going to be important to start today. We discussed last time DFS and the implementation of DFS in undirected and directed graph. We saw a couple of outcomes that we can get from DFS, and towards the end we saw how to implement DFS on directed graph and label every vertex with two numbers pre and post that we name, and how we can use the post numbers to classify the edges. In particular, we use this edge classification to discover how to classify a graph on whether or not it has a cycle. This is because of the last point, cycles exist if and only if DFS encounters a back edge, at least one. We made a clear classification of back edge, and we saw how we can, from one run of DFS, we can determine whether or not we have a back edge, and that in turn give us whether or not our graph has cycles. This is in the directed graph setting, which means that the cycles would obey the direction of the arrows, of the edges. And now I want to give you an example of a graph that doesn't have a cycle. Our eye may lie to us and tell us that BCED is a cycle because you see edges, but you can quickly convince yourself that there is no way to follow those edges in order such that you close the cycle. Graph like this we call a cyclic graph, and the definition is on top, but we will commonly refer to this as DAG for directed acyclic graph. Now there is something in this picture that I wanted to call your attention on, which is the fact that all the edges, the graph has been drawn on the map or in the paper, such that all the edges are pointing from left to right. It's easy to convince that, well, maybe the last edge, EF, is not really pointing to the left, but you can move F a little bit and you can see that there is a natural, if you want, like a flow of the edges going in one direction. And it's pretty simple to see this in this graph. But what if I tell you that this graph is acyclic because of the tiny little edges that are there are all they don't create a cycle, and I ask you whether or not you can create an ordering of the vertices such that the edges point in one direction. It will be a more complicated task for this graph to do this by hand or to even by simple observation. So I wanted to start by proposing an algorithm to decide, given an acyclic graph, how you can order the vertices in a way that the edges are pointing in one direction. I'm going to make that idea more precise in the next slide. So here is a definition of what we call topological sort of the vertices of a directed acyclic graph. So you're given a graph. Let's assume that this graph is given to you as a directed acyclic graph, so you know there are no cycles. And I want to order the vertices such that all the edges point in one direction. How we can make this precise? Well, I will say that the vertices of G are topologically sorted if I can order them, or I can label them, or I can enumerate them V1, V2 up to Vn in a way that if there is an edge between vertices Vi and Vj pointing from Vi to Vj, then the index I is less than the index j. For example, take the picture of the graph I showed you before, the smaller one, of course. I can label, or I can enumerate the vertices, or I can order the vertices in this order: A, B, C, G, V, E, F, and I claim that you can check all the edges are pointing from left vertices to rightmost vertices, and that is easy to check. That is what we will call a topological sort of the vertices. Now, it is important to have an acyclic graph, because if you have a cycle, no matter how you order the vertices, you always have to come back to close a cycle. So these topological sorts are only possible in a directed acyclic graph. One simple question that feels natural to me in this sentence is, given that I have an acyclic graph, how I can efficiently find a topological sort. As mysterious as this idea may sound now, if this is the first time you are thinking about it, we have already explored the ideas that will take us to an efficient algorithm to find a topological sort of a directed acyclic graph. And the idea is, of course, DFS again. Let me hint to you what the idea is. We discussed how we can classify the edges depending on the role they play in the DFS. And we saw that back edges has a distinctive property that make them special and allow us to identify whether or not we have cycles. And this property was that the post label of the initial vertex was less than the post label of the final vertex. Every other edge, when we run DFS, will satisfy the opposite inequality. And that is the key. If we have a directed acyclic graph, we don't have back edges, which means that every edge satisfies the other inequality. So let me summarize how we can efficiently find a topological sort of a directed acyclic graph. Well, we simply run DFS. Once you run DFS, you will sort the vertices by decreasing order of their post label. Why this is true? Why this will lead to a topological sorting? Well, every edge from U to V will be either a tree edge, a forward edge, or a cross edge. And that means that either of those edges satisfies the post label of the initial vertex is bigger than the post label of the final vertex. So if I order in decreasing order of the post label, I will go always from higher labels to smaller labels, which means that I have all edges pointing from left to right, which is a topological sorting. Now that we know how to find a topological sorting of the vertices of a directed acyclic graph, I wanted to mention a couple of important properties. The very first one, nothing tells you that there is a unique topological sorting. And that's important to know. We have found one possible topological sorting. It is not always true that we have a unique one. And most important, if you order the edges to go in one direction, there are two things that you should recognize by looking at that idea. First, the initial vertex in this ordering has no edges coming into the vertex. And the final vertex has no edges coming out of it. Those two vertices are going to be important. They have these special properties. So we're going to label them with a special name. That leads to the next definition. A vertex V in a directed acyclic graph is called a source vertex and respectively a sink. If there are no edges coming into the vertex, that means you are a source. Or, in the case of the sink, there are no edges coming out of the vertex. Again, with the example we have been using in this class, the vertices, for example, A and G, are both source vertices. There are no edges coming into these guys. The vertex F on the other side is a sink, because no edge is out of vertex F. Notice that every other vertex, V, C, D, or E, is neither a sink nor a source, because you have both edges coming into these vertices and coming out of these vertices. All these ideas related to topological sorts are going to be the key to develop an algorithm to compute or to get the strongly connected components in a graph. But first I have to define to you what it means to be strongly connected. What do I feel that I need to put this word strongly connectivity when I refer to a directed graph? And that's our next slide. In our previous video, I was telling you how connectivity in directed graph is a slightly more tricky, or if you want, more delicate than in the undirected case. And the reason is that you may have a path that takes you from one vertex to another, but that doesn't mean that you can return through that path to reach the original vertex. And that leads to the notion of strong connectivity. Here is the definition. Given a directed graph, we will say that two vertices U and V are strongly connected if there is a path from U to V following that direction, and there is also a path from V to U. So you need both paths in order to say that two vertices are connected. Let me give an example. Here is a graph, it's a directed graph. Let's check, for example, the vertex G and H are strongly connected. Why is that? Well, you can see there is a path from H to G. There is a direct edge actually connecting those vertices. And you can also check that there is a path from G to H through the vertex I. So these two vertices are strongly connected. Now, despite being an edge between A and C, you cannot conclude that C and A are strongly connected, because there is no way to start at C, following a path of edges and reaching vertex A. Since this doesn't happen, we will say that A and C are not strongly connected. And then immediately, the question of how do we find strongly connected components, in other words, subset of vertices that are strongly connected, how we can do that for directed graph. We easily saw how to find connected components on directed graph using DFS, but this is slightly different now, because if you follow DFS, you might get, for example, from A to C, and that doesn't mean that these guys are strongly connected. So we need to be a little bit more careful to handle, or to get these strongly connected components. The beauty, or the magic if you want, is that we can achieve this also in linear time, and that is the goal for the rest of the video. So the question now is, given a graph, how we can efficiently find these strongly connected components. And here is the graph from before, and I circled the connected components for you, just to, I think it's nice, and it's a nice example, just to realize how different components can be. They can have a single vertex that could be, a priori well connected, like vertex A, which have edges coming in and edges coming out. You can have a single vertex V or E, which are not really well connected. We only have a couple of edges coming out of these vertices, and you can have groups of vertices in each component, of course. Now there is something here that is important to notice, and it's maybe the first big idea towards the strongly connected components algorithm, which is the following. Say that you are given the graph and you have the strongly connected components just like this picture. Look at the edges connecting components in this example. I claim that you do not have a cycle that goes from component to component and come back to the original component. Why is that? Because that will mean that every component in that big cycle will be in a unique component. Everybody will be strongly connected, because if you have a cycle, every vertex in that cycle is strongly connected to every other vertex in the same cycle. So if you look at the components as big islands, if you want, the edges connecting those do not form a cycle. And we know we have a name for this. That will be an acyclic graph. We are only taking like bigger vertices if you want. So let's make that definition precise. Given a directed graph, consider another graph that I decided to use the notation GSCC for strongly connected components, that we will build from G as follows. The vertices of my new graph are going to be the strongly connected components of G. So every strongly connected component is a vertex in this new graph. How do I place the edges? Well, I will place a directed edge between two components S and S prime in that direction from S to X prime, if and only if there is at least one edge of G out of one vertex in S to a vertex in S prime. If you have many edges from component S to component S prime, you simply collapse, or if you want, you make into one single edge, and you keep that for this bigger like meta graph of connected components. In this way, you are building a simple directed graph, GSCC. And now this is an example of the meta graph. We have 1, 2, 3, 4, 5 vertices, and the edges connecting them are those connecting the components. If, for example, we have an edge from vertex I to vertex J, we will collapse that edge with this one and we'll create only one. It doesn't really matter where you start, because you are looking at the components now as a single vertex. It's kind of like taking all these vertices and making them into a big one. So it doesn't really matter where you start within the component, you are looking at this as a bigger graph. And we have discussed how this graph is a graph without cycles, it's an acyclic graph. We know a couple of things about a acyclic graph by now. We know that we can sort the vertices in a way that the edges are flowing from one side of the ordering to the other, and we know that we can label special vertices because of their properties as having only edges going out or coming into the vertex. So if the strongly connected component metagraph is an acyclic graph, we can label a vertex in this big graph, or in other words, a component in the original graph, as a source component or a sink component. And that will correspond to the same notion of source vertex and sink vertex. A component is a source component if it has only edges coming out of it. It's a sink component if it has only edges coming into that. For example, in the picture that we have of a graph here, the vertices V and E, or the components V and E, are both source components because edges are coming out of it and only out. The big component made of vertex Z, V, F, and J is a sink component because edges are coming into that component and only into. Now remember that our goal is to find the strongly connected components. And to build this graph, this meta graph, we need the strongly connected components. So it's kind of a loop to talk about finding the components and talking about an object that you need the components to build in the first place. But this visualization is actually very useful. And let me give you a hint. Imagine that you can identify a vertex in a sink component. Remember that a sink component is the one that has edges coming into it but not out. If you identify one such vertex in the original graph, then you can run explore from that vertex. And if you run explore from this vertex, I claim that you will only visit the vertices in the sink component. Why is that? Because edges doesn't exit the component. So you will explore and you will reach to all the vertices in the component because they are strongly connected, and you will never exit this component. So it will be great if we can identify a single vertex in the sink component, because that will allow us to run explore from that component and identify the sink component. That's a good first step. Now, this idea needs a couple of extra details to be complete. And for that, I'm going to present you another definition that may feel a little bit artificial right now, but soon I will tell you why this is going to be important. What is the role this is going to play? This is another construction we want to make out of the directed graph G. And this is going to be called or refers to as the reverse graph. This is another directed graph. We will get it out of G, and we will get it as follows. The vertices of both graphs are the same. It's the same set of vertices. Now you have an edge in the reverse graph from vertex U to vertex B, if and only if you have an edge in the original graph from vertex V to vertex U. In other words, guys, it's exactly what you think. You are reversing the direction of every single edge, and that's it. If you reverse the direction, we call that the reverse graph. Now, what is this definition important? Let me show you the next slide with a simple claim. I claim that if I have a source component in the reverse graph, that component is a sink component in the original graph. Why is that? Well, I told you this is a source component in the reverse graph. That means that edges in the reverse graph are coming out of the component. If I change the orientation of those edges, they are coming into the component and nothing goes out. So that is a sink component in G. So the meta graph in the reverse graph is flowing in one direction, and the meta graph in the original graph is flowing in the other direction. Of course, you are reversing the edges. What is a sink in one graph is a source component in the other graph, and vice versa. And I told you before that I want to identify a sink component in a directed graph. And a sink component is, say, at the end of this acyclic graph, of this acyclic meta graph, if you want. And if you're ahead of me on the game, you may be thinking that, well, I know how to find a topological sort. I know that my last vertex in that topological sort is a sink component. So I can, run a DFS in the original graph and get the vertex with lowest post label. Maybe I know this may have cycles, but maybe this vertex is in the sink component. The problem is that idea is actually not correct. And because of that, we need to introduce the reverse graph because of claim 2. This was claim 1. You reverse the role of the components if you move from the reverse graph to the graph itself. Claim 2 gives you the following. Take V to be a vertex with maximum post label after running DFS in the original graph, G. then V belongs to a source component. This is true. If you take the vertex with the maximal post label, that guy lies in the source component. In the component of that vertex, you only see edges coming out of it. And the proof of this claim is not as easy to present as the previous claim. And my suggestion is, if you're curious about it, take a look at Professor Svigoda's video. It's the same video I recommended for Tuesday. This is the same video. It's a video talking about strongly connected components. In that video, he goes into details about this proof. I am not really that concerned that you know this for this class, but you should remember this claim because it's placing you in a source component in the graph G, which means that it's placing you in a sink component in the reverse graph. And let's now try to put all this idea together to build an algorithm that provides to us or outputs the strongly connected components of a graph. So here is the summary of these ideas and how we can put them together to cook at our design. I want to find a sink component of G. More precisely, I want to find a vertex in the sink component. If I do that, I can run explore from that vertex and I will get that component because the edges out of this component doesn't exist. I will never exit this component. How I can do this? Well, I will run DFS on the reverse graph. I will first build the reverse graph and I will run DFS. I will get the vertex V with the highest post label. By claim 2, this vertex V lies in a source component of the reverse graph. But that means, by claim 1, that V lies in a sink component of graph G, the original graph. So now I found a vertex in the sink component. I can run explore from this vertex and I know that I will visit exactly the vertices in the same component, which is the sink component. Now imagine that you are at this point. You have identified the sink component. What happens if I drop this component from this metagraph, or if you want from the graph G itself? That means that my next component will take the role of a sink component. Imagine that you have an ordering of the components, because this is an acyclic graph, this metagraph. If you drop the very last one, the one before will now will take the role of the sink component. So now the highest post label remaining will be in this new sink component. So you can run explore again from this vertex. And then you keep doing this, identifying the components from the sink all the way back to the source component. And that is the strongly connected component algorithm. So let me summarize that for you. It's actually quite simple. How we can find the strongly connected components of a graph? Well, we built the reverse graph, G. We run DFS on this graph. We source the vertices by decreasing order of the post labels. That means that the very first one is the one with highest post label. Now we run DFS on G. That means that I'm going to start exploring from the highest post labeled vertex. Just as I told you before, this is in the sink component, so I will first explore that component. Only when I am done exploring that component, I will jump to the next vertex, which I know now lies in, well, the last, or like the one before the sink component, which is kind of a new sink component. And I will run explore from there and I will discover the new component. And then I keep doing this until I have correctly labeled all the components. If you want to keep track of the components, an easy way to do this is to use the implementation with the CC clock. The same implementation you use for undirected graph will allow you to identify the strongly connected components. But the intermediate step is key to sort the vertices in decreasing order of the post labels after running DFS on the reverse graph. Now, why this is linear time? Well, I hope you guys can take a minute to see that all these steps will take linear time the most. If you have to build the reverse graph, you only have to loop through the edges and reverse the orientation, and that will take you linear time. You know that running DFS takes also linear time. Of course, sorting the vertices is just looping through the vertices and assigning the position if you want. And then you run DFS one more time, which is also linear. So the running time is indeed linear on the size of the graph. Last but not least, I wanted to tell you about deers in Cuba. We call these venados more often. We also call it ciervos, but venados is like the common term that we use in Cuba. They are not very common, but you may find the white-tailed deer if you really want to search for animals in Cuba. That is the word of today's video, and I see you guys in the leaf section.